Session being recorded. Time to start. And if you can say got it over there too.
Oh, yeah.
And I'll be taking notes on my phone, so don't get, I'm paying attention, just
Notes on the phone.
notes. All right,
Okay. All right. Hello, all. This is our critical design review for the GhosTalker project. We are a team for the Ghostbusters. Our team consists of me. I'm the team leader and overall helper.
your name?
Sam, that's Sam.
I'm Cole Helbig. I'm part of the data acquisition team and stimulus presentation team.
I'm Surya Gupta. I work on the machine learning side.
I'm Jason Moore and I work with the EEG headset design.
So the motivation, needs, and stakeholders of the project. This project pertains to people lacking the neuromuscular capability to communicate and communicate verbally or physically, and proposes a solution that works for all users regardless of the level of physical disability. The needs of the project are a robust stimulus presentation, having a program with effective outside noise removal, and consistent, accurate classification of phoneme data. The stakeholders of the project are Dr. Rocco, Dr. Kudzia Tamina, Dr. Saeed Ziafard, the Ghostbuster team, doctors, patients, and researchers.
Some existing solutions are the first one that I found was called a P300 speller. It uses EEG to allow a user to spell out a word. This isn't a perfect solution. It takes a lot of time to spell out a word and leads to a lot of fatigue with users. So it's not viable for long-term use. Another solution is invasive invasive implants that do pretty much what we're doing, except it's much more expensive, requires surgery, and can lead to health problems from surgery health problems.
All right, so I'll take you through our requirements table. Not much has changed since the last time we spoke, but we still have, one of our requirements is an engaging stimulus presentation, and ideally it'd be 180 minutes long. On the data acquisition side, we want a signal to noise ratio of about from within 15 to 40 decibels, but ideally 40 decibels. We want accurate classification, obviously that's the goal of this project, and ideally 65% accuracy is what we're shooting for. Our AUC of the receiver operating curve, which is a metric of precision to accuracy, we want that to be at 0.8. And then our F1 score, another metric of precision to accuracy, we want that to be at 0.65.
All right, so moving on to the constraint table, we're required to use EEG for our method of data collection. We have to use the OpenBCI sites on board and Mark IV helmets. There are 16 channels on the helmet we have to use. We have a leftover budget of $500, and the lab is only accessible during work hours, 9 a.m. to 4 p.m. So now I'm going to talk about the EEG headset itself and the three main electrical components. So here on the left, we have the sites on board. That's what's actually collecting the electrode data. Here in the middle, we have the Wi-Fi shield. This allows us to connect our board directly through Wi-Fi instead of using Bluetooth like we previously used. And then here we have the V3 DAISY module. This sits right on top of the sites on board right here and expands its capabilities to allow for 16 electrodes instead of just 8 electrodes. So a smaller battery pack saves space and time. One of the main flaws with our original headset was this huge bulky AA battery pack on top. Not only that is when you're using AA's like that, sometimes you'll forget to turn it off, and then overnight all of your batteries are dead and you have to spend a bunch of money replacing them. And also the batteries weren't really accessible right here. You see there's tape over top of it. So every time we'd have to replace the batteries, we'd have to take all that tape off and then replace it, and that was a whole like 15-20 minute process every time. So we don't want to be doing that every time we want to use our headset. So instead we switched to our 400 milliamp lithium ion rechargeable battery. This fits perfectly in the headset right underneath the board in here. So it's all housed in there. And then the cable sticks out right here. We can leave it in for recharging and everything.
But if you're showing something on the outside, because there's light here, he doesn't see.
Okay.
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 Sorry.
So this is the 16 electrode placement that we ended up sticking with. Like I said before, you have equal electrodes on each half of the brain, and the sites on board is placed directly in the middle at CZ. So here we can see some images of our fully assembled headset. On the diagram, you can see the sites on board is on the bottom. The Wi-Fi shield stacks directly on top of that, and then the DAISY module stacks directly on top of that. Also, if you see the orange little clips all around the headset, these are 3D printable wire clips. They made wire management a lot easier, and just all in all helps us organize our headset. So some lessons learned I learned from the headset is simple solutions can save a lot of time and money with just that simple $5 rechargeable battery. It saves us a tremendous amount of time and money with replacing batteries. And also wiring is surprisingly fun. I didn't used to like it at all, but this was fun. So.
So the next part is the stimulus presentation. Our code for this does a little bit more than just presenting phonemes. It also controls the sites on board. So the first thing that the code does is connect to the Cyton. If it can't connect, it just terminates the program. And the code just loops through trials for 10 trials of each phoneme. We decided to split up. Instead of doing 10 trials at once, we do 5 trials at once because we want our data to be more accurate, and doing too many trials over and over again can decrease the accuracy of our trial data. And then the code just sees if we've tested every trial 10 times, and if it does, it releases the OpenBCI session and exits the code. So what we call a block is just the set of 5 trials. So once we start the block, we first introduce the stimulus through visual and audio representations, and then give a small waiting period before we start the actual trials. Once we do actual trials, each trial lasts 2 seconds with a 1 second wait period in between. And when the trial starts, the OpenBCI is triggered to start collecting data. And when the trial ends, when 2 seconds is up, it just sends a signal to kill the trial. This has led to some problems that I'll discuss later on. For the validation, since there is no real outside data that we can use to verify that what we're getting is actually good data, we're going to test different trials of the same phoneme against each other, and see what the variance is between those trials. If we have a high variance, then we know that we have to fix something. And then we need consistent samples per trial. It makes the machine learning a lot easier. We've had some problems with this too. We want 500 samples per trial because the OpenBCI runs at 250 hertz for 2 seconds. And on the next slide, we have not been getting 500 samples. We've been getting something around 3,000 samples, which is around 6 seconds per trial. I think the reason we do this is because the code just waits for 2 seconds and then triggers the OpenBCI Cyton to stop. Instead of this, we're going to allocate memory for each trial so that we can only use as much memory, or allocate memory for each sample so that we have only enough memory for 500 samples, and then that kills the test. And that should fix our problems with that. Oh, so
Transition.
and now Serena will show the machine learning, which uses the data collected from the stimulus presentation to classify phonemes.
Right. So I'll take you guys through the machine learning pipeline and a general overview of it, but before I do that, can I just ask if anyone has any quick questions on anything discussed so far?
Oh, I have, but I'll ask at the end.
Okay,
Yeah.
gotcha.
We'll ask at the end.
Sounds good. So, the machine learning pipeline refers to the set of steps that are able to process the raw data that the data acquisition step has provided, right? And so data collection here refers to data aggregation. How do you take that raw data and are able to aggregate it such that you can classify it at the very end? And data collection, it just refers to like aggregating that raw data. Pre-processing refers to notch filtering or, you know, any kind of like bandpass filtering you might want to do, but it's done to time series data, which I'll explain in next step. Feature extraction then refers to how do you take this time series data, which again, I'll explain further, but then how are you able to derive some metrics that you can use for classification? And finally, we get to classification, which is training a model on this data that you've collected to predict how a new sample, which phoneme that sample might be. Okay, so now I'll walk you through the data collection and pre-processing phases, right? And two things I'd like to define before we move on. An element, this is something we define internally. So an element is a patient, one single combination of a patient, trial number, and phoneme. So say we have, you know, we're only wanting to classify 3 phonemes and we do 2 trials for each phoneme for 1 patient. One element is, you know, say we do phoneme 3, trial 2, patient 1, right? So this is what the data will look like when we're actually working with on the machine learning side, right? You have 16 channels of time series data. And the second thing I want to define, by the way, is time series data. Time series data refers to data that has timestamps. So we're getting data that has 250 samples for every 1 second. That's all timestamp data. And that's not fit to be classified. A classifier cannot work with that kind of data. So we have to do something to it, which I'll walk through. But when we get this kind of data, the first thing that we do is notch filtering at 60 hertz, because there's known to be a 60 hertz disturbance where the recordings take place. And so we want to try and drive that down to 0. Then the second thing that happens is there's this discretization of all of the channels. So there's 16 channels of time series data. And these channels are then discretized, right, to create these windows. And this will then go on to feature extraction, which is the next step. So now in feature extraction, these channels that we discretized, now you're able to take this time series data, which is again, you know, 250 samples per second, and you're able to derive some kind of metric from them that you might want to use, such as the mean. The mean is what we're using for preliminary testing. Later on, we plan on using the DV2 wavelet transform and the first 4 central moments of mean, variance, kurtosis, and skew. And right now we're just using mean. So this is what the data will look like at this stage, right? Where we extract a singular value from multiple data, from multiple timestamp data. And that's how we convert time series data to stationary data, right? And this is what the feature extraction stage will look like for the data at this point. Okay, and then we move on to classification. So one more thing I'd like to define is lag variables. This is common practice in industry when you have multiple channels of data or you have, you know, some time series data. What you would want to do is, because when you want to train a classifying model, you need a vector of data. And the matrix that we had previously, you can't train a classifier with that. So all we do is, in the previous matrix where we had 16 channels and n number of windows, we take each channel and concatenate it onto a 1-dimensional vector. And so you're able to take the dimensionality of the previous matrix, which was 16 by n, and now you have this one-dimensional vector. And this is the final form of the data for one singular element. So if we extrapolate these steps for all the elements that we have, this is the final form of all of the data now, where you have this one-dimensional vector representing one singular element, completely like pre-processed, representing the extracted features such as the mean, and you're able to collect all of your element vectors, assuming that there's k elements, and you would need a corresponding vector of their identifier. So 1 through 44, which phoneme is this? Which phoneme is this element 2, you know? And this is the final form of the data that then you can then feed to a classifying model. And what I've actually learned is that the emphasis is not so much on the classifying model as it is on the pre-processing and data aggregation steps. So for classification, we decided to broaden it back up. Instead of focusing solely on support vector machines, we're planning on using multiple different classifiers and see how that works with our different feature extracting steps, right? So we're still planning on using support vector machines, random forest regression, and linear discriminator analysis for classification. Finally, this is our validation step. And so this is to test how accurately and precisely our model is able to classify these phonemes. This is, again, common in machine learning industry. It's called k-fold validation. And so what this does is, assuming that you have a total set of data, you're able to discretize your data into 5 total pieces, right? And then 4 of those pieces are used to train a model that has never looked at the last piece. The last piece is then, the model is tested upon the last piece to derive some performance metrics. Then you iterate and you rotate which group is a testing group and which group is a training group until you have moved through all 5 or all sections of your groups, deriving multiple performance metrics. These performance metrics are then aggregated into a receiver operating curve, which we discussed earlier. And the area under the curve can then tell you your precision to accuracy. Machine learning side lessons learned. There's a lot more planning and organization that needs to go into understanding the forms of data as it moves through the process, and understanding the requirements of the model itself, that the model can't just take time series data. The model can't and the model has certain assumptions that it makes about the data. So those assumptions have to be understood before you actually feed data to the model. That was the biggest thing learned. And the second other thing that was learned is that there's a lot of internal coordination that needs to happen when, you know, data acquisition is giving raw data. It has to be labeled in a convention such that when the files are collected, it can be automated. The files can be automated and collected and aggregated and classified. Yeah, that's all on machine learning side.
So
Now Sam will talk over management.
So as we see, most of this was our last semester Gantt charts, or last presentation, PDR, prior to the PDR presentation on the Gantt chart. Then as we were going along after the PDR and stuff, we continued to add to the Gantt chart. There were a couple tasks added in here after the PDR, such as revising and rewriting, then writing chapter 3 for the detailed design review. Then we also add more miscellaneous stuff, hopefully getting the virtual environment set up and get the GitHub set up, along with getting our IRB training done by January 10th. That way, when we come out of break, we have that also done. Then also, as you know, Jason talked about the headset and how we got a new rechargeable battery, so we had to spec that and all the stuff in Gantt chart. That was all done as the headset is now assembled, and our students presentation had a lot more tasks that we added to it throughout the semester as we're going along to break it down into easier steps for us to understand. And our milestone chart has been expanded and also has had some date changes. The classifier training, working machine learning code, and ground classifier trained, that's taking longer than expected. So the date has been changed to hopefully having all that done by January. And then we also added the IRD training, optimizing the code with the automated stimulus presentation, as Cole did talk about, that currently it's sampling at 3,000 instead of the 500 that we need. So that's taking 4 extra seconds.
Yeah,
Right.
about 4 seconds more than we want.
And then hopefully we start our feature extraction. This unit's presentation with audio can hopefully be finished by like the second week of the spring semester. The cost estimation has been added to only a little bit. We all had the rechargeable battery and battery charger. Originally, this was going to be spec'd out and we're going to be ordering this, but they were in the lab and they were provided by the lab for the project, so they did not have any initial costs for us. Lessons learned, there's a lot of work that goes into project management and organization. And I realized like my internship, I only got like I worked with the projects and stuff, but like I didn't see how much management goes into it. It's a lot of emailing at times and making sure everybody stays up with their tasks, because it's sometimes difficult keeping up with everybody and what everybody's doing as they're all working on their own projects. Does anybody have any questions?
Thank you, that's good. Very good. First of all, congratulations on your presentation, especially machine learning. I actually now understand your train of thought, so I can follow up easier. So it's very, very, very helpful. Do you have demonstration that you want to do before questions?
Yeah, we do.
Okay. So usually I ask the student to do the demonstration because some question will come up during that.
Yeah.
Or some will be answered, you know, if it was left out. So, yeah. So what's the process of the presentation? Yeah.
Um,
Can you join the Zoom and then screen share?
no, because I have to connect to the Wi-Fi shield and I
Can't have two sources of one.
yeah, which
So for us, you can show the screen so me and Dr.
I can
Tamina
connect-
will see it.
I could connect my phone so that you can see from like.
Yeah, and,
That's fine.
yeah, we can do that. And then so you can kind of a third video, so.
Right.
Yeah, so he can, Dr. Loraco can see.
Should
And
I stop this share then?
yeah, you can start sharing.
all right. Can you turn the Wi-Fi shield on?
And then once Sam's phone is connected, I'll make that one to be the main display.
Sure.
Well, no, I will make this one to be main display. To see, we'll see what we can do. Sam is here. Okay, I can see. Jerry.
Recording in progress.
Oh, you have to. Turn off the speaker.
Right. And then. Microphone's already muted, right?
Cool, are you connecting?
Still connecting. It takes a while to connect to the
It's okay.
Wi-Fi shield.
So when I was saying, so when you are in front of the
Yeah,
screen, Dr. Lorica can't see because there's too much light.
Right.
So if you can say, yeah, I think you're there, he can actually see.
Yeah.
Yeah.
My bad.
All right, I'm ready whenever you are.
That's
Maybe
fine.
bring that closer. I'm not sure if,
So you can be where Sam is staying because he would all still see it.
I can still see the headset, yeah.
Yeah,
okay.
yeah, and I can make, yeah, if you talk, then the headset would be
This
I
will
can
be
see
stuck.
Sam's phone.
different.
You have a back camera?
Well, we're having changed the camera.
Yes, well, I see Sam up close.
All right, we ready?
Let's go. Do you want to turn it around? They could see
I
it.
can make this one to be spot.
So you can turn it around so they could see it instead of.
There.
I can see the screen, yeah.
Yeah, that's better, but keep it there.
So once the trials actually start, you can see it goes way longer than we want to.
Mhm.
I think it's just because of like the delay between the actual command being put out to stop the open BCI and it actually getting to the open BCI.
Yeah, so could you make that faster using, like, because your board might not be fast enough also, or you have Wi-Fi?
The board should be fast enough. I think it might be because of the Wi-Fi.
Yeah.
Well, if
because
I
see
may,
it's actually Related time delay. Yes, John, sorry.
If I may add something, Python, which you guys are mostly coding in my knowledge, isn't exactly the most efficient implementation level language when it comes down to it. So also beware of using commands like wait or sleep in Python when you're talking about hardware, because those can mean very different things. So the technique that you mentioned earlier with the memory allocation is actually a good move to counter that.
Yeah, so, yeah, we do use sleep right now,
Mhm.
which obviously isn't the best
Yeah, okay.
option.
Because if you can take some of the delays out, you get closer to, you know, the 2 second or 500, minus
Yeah.
3,000 is like really extra the information.
And something Dr. LaRocca mentioned was that if we want to take this to a real-time system, allocating memory would be much faster for that.
Yeah,
Uh,
so, did this have like a sound?
I wanted to code that in, but as I was changing it, I realized I'd have to change my code and I didn't have access to the helmet at all. And if I run my code without the helmet, it just terminates.
Okay.
So I'm
It
going
has to have the
to,
Wi-Fi module.
Hmm.
It has to have my Wi-Fi module.
yeah,
And the board.
if it doesn't connect, the
everything.
program
It sends
doesn't.
commands to the operate the board.
Does the board have to be connected to the sensors too?
I don't think so.
No, because then it starts reading EEG data just from the pins, like.
Okay.
It's like right here, this is the data is coming in. So I mean, he probably could just take the board or something.
Yeah,
We'd
that's
have
what I
to-
was thinking.
we might
Yeah.
have to
But
disassemble
It's not gonna work over the break and then you come back, so.
Yeah.
And I want to correct you on access to the lab, no 9 to 4, not anymore.
Yeah, we were talking
Right.
about that while we were preparing.
24/7, anytime you want
Right
to come
next
to
to
lab,
this. area.
yeah, I'll give you have access. So this was, so because you're talking about the constraint, now you're not constrained anymore.
Well, we have the constraint up until the CDR. so it's like- That's all I saw.
Open the door for them anytime you're not, but okay.
We felt bad about asking. It's fine now.
It's not so bad, it's just a one floor, okay,
All right, I think we,
so, yeah, I think- yeah,
I saw the demo. Good job.
yeah.
So now we can get to questions. I'll let Dr. Z and Kudzia go first.
Yeah, so one question before we start about the, so, the data you collect, you go to that software you showed me before, right? And
Yes.
then,
It's like,
since we don't have the machine learning modeling done, like, we already saw that part.
right,
So we saw, and is that part done? So I just want to like get an approval from Dr. LaRocca that this, was that OpenPCI, like a software that's on your computer and shows all the
Yeah.
data?
yeah,
So is everything with that part done?
I don't think so, yeah. I
Is
think we
it-
need to cut down on the
Does it need to
sampling.
be calibrated?
Yeah, I think that's really what needs. to be
So,
done.
so what I would have loved to see was your plans for testing things, for example, calibration of that OpenPCI. This doesn't need calibration, right? This just shows, or do you like ask your reader to or your audience, like the person that's being tested, to look at some things before the test? Like when they sing a song, they say la 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 la, something, you know, to calibrate everything for
that could be
themselves.
something we did. We did something kind of like that,
Okay.
where we just
We
told
just
Sam
wanna-
to think about nothing and then think about something.
Yeah.
And we did get like a,
Yeah,
You
I
were
think
there,
that should be,
yeah.
that should be a calibration process, because it was very interesting. Maybe I
Yeah.
asked you to not think about anything, then think about me, and think about something you like, and then we saw all the wave. So before start testing, because next semester is all testing. Think of calibration, your way of calibration for everything. So you know that we did this before we started. So you have a point, right? That you can always say, everything is based on what we did at this is our zero. Everything is based on the zero that we created. And then, you can add those to your to-do list, because there's a to-do list that
Yeah,
you
I'm adding it
submit,
to my
right?
outside table right
Yeah, so
now.
that would be like initialization for testing, what you need to do before you start thinking about tests. All right, now I'll,
Yeah.
leave.
I think one way to answer that question would be to have some training material for the subjects when they start. You don't just throw the stimuli to them.
Yeah, that's.
There
what-
will be some training session and then they start the
Yes.
stimuli. I would just hope that this is our plan.
Yeah, so they
Yeah.
know, yeah, what to do, right? So otherwise, the first few data will be wrong because they didn't know what to do,
Yeah,
right?
definitely. We'll start off with a baseline for each subject and
Yeah.
then we go off
I
of that
really like that.
baseline.
I think that's
That
a very
becomes your
good plan.
control
Yeah.
and then whatever you collect after that goes off of that.
I
control.
really like that, yeah.
Mhm.
Yeah.
I had one question on if you could go back to the slides. I don't know if it's possible.
Yeah. I can do that.
On the machine learning part, I have one quick question. Is the number of channels gonna be the same as N? Because you have subjects, then you have channels, and then you have, I think, timestamps.
Yeah,
I just wanna go back to that.
I got-
For clarity,
yeah.
maybe slide number 17.
Are you talking about this one?
Yes, absolutely.
Is it N based on what our window size is?
Yeah, so if you go, actually, like, go back
Yeah, one more
Vertical
slide
slides.
maybe.
one more. Okay, so
Yeah.
this is like where it begins.
Yes.
Um,
So we have 16 channels.
Yeah.
And then you're breaking it down into windows.
Yeah.
And you're breaking it into N windows. Is N same as K in the next slide?
no, so N is the number of windows per channel.
Per channel, yes,
So this is like how, and this is like a parameter we still need to test, right?
right.
But if you go to then the next slide,
Mhm.
the one after this.
One after, yes, the.
Okay, so
this one.
K is number of all the combinations of trials, phonemes, and patients.
Oh, I see,
So
okay.
that's what
okay.
an element is. and We
Mhm.
have K elements then, so,
And you still have N by one
yeah, so
of
actually,
16 channels, you kind of concatenate it.
exactly,
And then you have different combinations.
exactly.
K
So the
combinations.
total dimension of this vector is
Yeah.
actually N
Mhm.
times 16 by
Really good.
one.
Okay, thank you, that clarifies.
So two of my questions were actually on the timing and data rate that you're gonna use memory allocation for that, right?
Yeah.
So for on slide 18, you talked about mean. Yeah, so again, assume I don't know much about machine learning. So let's say you're gonna use different methods, right? One is mean. Would this be like a frequency? What would like what's the nature of this data?
Yeah, I can mention that. So right now you have, you have like some kind of wave of data, right?
Yeah.
And you've discretized it, so you're only looking at a certain portion of it.
Yeah,
The mean is just the average, like
is that
Amplitude.
frequency or
not in
amplitude?
frequency, not
Amplitude,
amplitude,
okay,
amplitude,
all right, amplitude.
just the average
Okay,
amplitude.
so
across.
would you, so whenever you're, so this is different methods that you can run through the model, right? And then you plot them or like you continue everything that you show. Are you planning to do all these methods or you're gonna pick, like, I'm gonna do mean square, S cube, like, or regression?
Yeah.
Are you gonna pick or are you gonna do all of them?
We plan on doing all of them because it's not hard to switch out what you're doing. It's just a
Okay.
function you have to apply.
And they all will be amplitude,
Yeah,
right?
they will all
And
be
based on amplitude, you can, because I think is next slide, you have K of the
Elements,
elements, right? So everything in the elements
Uh-huh.
is also based on amplitude?
Yeah.
Okay, then you can compare, right?
So this is what makes like those K elements. Like this is like.
Yeah. The nature of, I wanted to know, like, if the phonemes, because they are. For like right now is a letter or something you think about, but in your brain is frequencies, right?
Right,
And out of that frequency, you're only looking at the amplitude of that frequency. You're
Right.
not looking at anything else,
I see what you're saying.
correct?
Yeah,
Is that sufficient, or do you need to look at something else? Because usually for waves, we have frequency amplitude,
right,
right?
Right.
So, are we looking at the other part of that as well or not?
so,
Because if you use Fourier transfer, think about that, you're using frequencies,
Mhm.
right?
Yeah.
So you're taking like a part of data out and not looking at it at all. I'm not sure, I'm asking
Yeah,
if
yeah.
that's a safe way to go or not.
so
Yeah.
this is based off of the research that we did in the initial phase, that
Mhm.
we found like people were trying to find multiple ways of feature extraction, but the two that we found the most were, the first four central moments and then the DB2 transform, which is like a wavelet transform, which actually does involve like some frequency analysis. But we're still planning on converting it even after doing the DB2 wavelet transform, it's still gonna
The amplitude.
be an amplitude, yeah, like we're still gonna convert it back into time domain.
So now one question, what is the variation of amplitude you expect? Like from like, different phenoms, like what amplitude they have?
That's it's so hard to observe like things like.
Because I can't, so it's like time domain and frequency domain and S domain. I
Yeah.
live in time domain, I understand time domain.
Right.
I don't live in the other two domain, right?
Right,
So it's very difficult to experience it or feel it,
right,
so I need to understand it. So I don't, so now I get it, that this phenom, we're mapping it to some amplitude.
Right.
Right? Whatever you think, it's gonna be corresponding to an amplitude.
Right.
You're taking that feature, right? You're extracting that.
right,
Now, usually when we see a data, one way of even validate, like even before validation, to say if does this make sense? Is
Yeah,
where does this data land, right?
I see.
Is it like above, beyond our expectation, or it is within our expectation?
Yeah.
Where is our expectation?
I see.
Do we know that, or that's part of also your study, or
That's
those
not-
paper have something?
That's not, we haven't found any papers like that, and that's not what I'm doing, but that's actually something Cole mentioned in his step of data acquisitions, validation.
Mhm.
Like, I think that's what you're referring to, is like the data that you're collecting, is it valid? Is it off variance, right?
Yeah, so you collect data, right? So that's data. To me, like if I look at you show me amplitude, let's say it's 2 months from now,
Yeah.
I say, Dr. Z, here's our result, and I'm looking at some numbers.
Uh-huh.
I want to know if that makes sense, but I
Yeah.
don't have that sense because I don't know. So it's like, cool, you have some numbers, but I don't know if these numbers are
Yeah,
within the acceptable range
I
or
see,
they're way off. Let's say that, oh, what's the distance from here to my office?
right,
560 miles. No,
Yeah.
no, it can't be that. You know, I want to get that gauge.
I see what you're saying, but for things like, so for your office, like, we live in that world, right? We can see like how, like,
Exactly.
But
So I
like for
want to
things
know
like
in
this,
that,
yeah.
in that report, how do you do it?
especially like, and I wish we got to show you, like, that's actually something we were planning on doing. Was like showing you what our raw like data actually looks like, right? You can see that like. It's really hard for us to understand what the variance of this might be like and what the ranges look like, and especially the differences between the phonemes. Like, it's so hard for us to distinguish this, and that's why we're turning to machine learning, you know? Like, it's so hard to observe.
Okay, what is let's say machine learning will
Yeah.
give you something output,
Yeah,
right?
yeah,
You should be able to understand the output because you're gonna write about it. If you don't
Right.
understand it, how are you gonna write? How are you gonna justify what you did?
so the output's gonna be like, if you give it like a new sample of like,
Mhm.
you know, someone's like time series data. And you run it through these steps and you're able to get this vector, then
Mm-hmm.
it's able to say like the output of that is gonna be 1 through 44. What phoneme is this? That's the output of that, you know?
Mhm.
And the way it does that is like. This is like how the algorithms actually work, is like, you're able to like create like, if you have multiple dimensions, right? If you have like multiple dimensions of features, all of these features like have their own dimension. And so it's plotting these features in like higher dimensions,
Mhm.
right? And it's able to create lines separating these features. These are like the hyperplanes, that's what they call them, is like separate these features. And it's finding out like whether it lies on this side of the line or this side of the line, the new point. And if it lies on this side of like this line, then it means it's like class A. If it lies on this side of this point, line, it's class B. Does that kind of help?
Yeah,
Like,
it also helps because now I'm thinking, that's why you have like in your element, you have the patients as well, because not everybody think the same way.
yeah,
So their model would be
Yeah,
different, but it's
exactly.
trained again. So for them would be, so the amplitude for one person might be different from the other person.
yeah,
So you actually don't know,
right,
and you leave it to the model, and you're not
Right.
gonna look at it,
yeah.
right? So you trust the
That's what we
awesomeness of
have to do, is
technology.
we have to trust the fact, right? And like, that's the other thing that
I
you
get-
mentioned,
I-
yeah.
Okay, cool. John, now you can ask.
All right, a couple of points. To kind of follow up with Dr. Z's points earlier, one point that I think would have been helpful is that I know you're mentioning mean as your feature here, but because the data is what format is the data being saved? Because it's being saved in its raw time series form, you could do any kind of feature extraction you want afterwards, in addition to what you're already proposing here. Because as you guys explained about trying out the different machine learning models, once you do the offline analysis, you really can change it up however you want. So change Fourier transform and mean, it may not necessarily be mutually exclusive. Here I see you're going with mean because it's been used in a couple of papers, but future analysis and future work can be adjusted very easily with the framework you're proposing, something I like. So machine learning, I think, is well organized. A couple comments on the other sections. All right, for market and demand, I know you mentioned invasive versus the P300 speller. So if you had some pictures or a little bit of supplemental data on each one, like here's a brain surgery of an implant chip or an immune response, or if you have something like, oh, this is the ungainly, horrible P300 interface, those would have been very helpful in showing like why something like this could be much more intuitive once it's calibrated for a subject. Another point on the headset. I appreciate the breakdown of the different boards and their functions. Something that also might be, I also really liked going from the LiPo battery compared to the crappy AA. So something else that might be helpful would be like, okay, how long can it potentially record for? How about how well does it play with the Python scripts you're working about? You've mentioned that before, but maybe a bit more about how the board can play with the other software in the system. That would be a very useful thing to include as well. Also, maybe a bit more of a top level thing about how all this kind of flows together or fits together. Maybe just a little block diagram. Nothing too exotic, just kind of help break down the areas of responsibility for each domain here, because this is a very complex project, as we've all discussed. So all that would be helpful. So the range of each variable, likewise, is going to be something we don't know yet, because it can vary even within the same subject and within the same phoneme. So that's something that we need to determine every time we collect data from a particular individual or circumstance. So as Soraya explained, I think fairly adeptly, it's like you try to throw everything into a giant multi-dimensional, high-dimensional model, because sometimes you can't visually determine class 1 versus class 2 just because of how noisy the data can be, and you need to aggregate lots of it to have any meaningful outcome. One question that also might be helpful for Soraya is, are you going to go with 1v1s for your, how are you going to rate the classes? What are you going to classify 44 at once? Are you going to classify one class versus all others and just kind of rotate them around? Are you going to do a bunch of 1v1s, like phoneme 1 versus phoneme 2, or phoneme 1 versus everything that's not phoneme 1? 1v1 versus 1v all. Those would be helpful to include in there as well. Of course, it doesn't necessarily need to be mutually exclusive, but what have other researchers done, or what approach do you guys think would be the most valid for this circumstance? I think that would be helpful. So just my comments thinking out loud, but other ones would be, I know we don't have the auditory feedback, but when do you guys plan on actually start trying to collect some test data with the protocol, assuming you can solve the memory allocation issue with the delays and latency early next semester?
So are you saying that, like, are you saying that the data that we're taking would be good data, or are you saying like data that would be taken would just be, once again, like test data?
Well, for now, let's just assume it's test data, because calibration, now, there are ways to do calibration or validation. What about artifact rejection or stuff like that? I know you're doing the notch filter, but what about, I know eye blink detection and jaw clenching and other sources of noise in EEG. We haven't really gone over that much, but something worth might you think of or consider a couple of alternatives or ways to work around those if possible? Sorry if I'm.
Can you repeat that one more
Sure.
time, please?
Sorry, I'm talking a mile a minute here, but basically, as was mentioned earlier, there's the calibration or at least validation of the data you acquire to make sure it's correct.
Mhm.
You have mentioned that you would look into the variability of each phoneme or correlation of each phoneme within class, right? But what about cases where the data may be contaminated with things like interference or artifacts like eye blinks or jaw clenches, which can interfere with an EEG headset or subject moving the headset around or fidgeting?
So
Like, do you have noise canceling?
I mean, there is filtering within the open BCI GUI. That's mostly just like 50 to 60 hertz bandpass filters. So like, overhead
Yeah.
lights or whatever else, can
Yeah.
throw off our data. That, like, I think we should have that like already in our data as soon as we print out.
Dr. LaRocca, so two things that we're doing, and you tell me if like this doesn't cover everything, right? Or like if you have like if you can see how what we're doing might fail. The two things that we're doing to account for what you just mentioned are, first, what Cole's doing is that any like for within each phoneme, right? Any like, what's it called? Like, I don't want to say data, but like any like point, I guess, that like has a variance that falls to outside of the group, we're gonna classify. Like, we're gonna say that that's like not valid, right? So we're gonna reject that. And you can do that like to prove that it's like statistically significant. Like, there's like p-tests you can do for that, and you can do that in R. That's one thing. The second thing that I was planning on doing, but I haven't like mentioned it because I don't have a plan for it yet, but I was thinking about it, was we were thinking about like taking a raw like before you start every recording session, just have like a 5-second sample of like what the ambient, like what is it, like it's ambient, like
noise spectra, basically.
noise background is like, right? And then use that to filter out like literally overlay that on top of like the signal that we collect to drive that noise down.
Mhm.
Does that, is that like an adequate solution to that problem?
That could be one, and there's also one that could, there's also some of the stuff that could be done pre-processing or post-acquisition pre-processing.
So
What-
what,
Yeah.
what techniques in mind, do you have in mind for that?
Oh,
Yeah.
Oh, yeah, I was like,
Oh, simplest one would be, what about some kind of baseline removal or something to that effect?
is that what I just mentioned? Like where you take a,
You meant, there's different ways of doing baseline removal.
okay,
Taking what you were describing, at least I had thought of it or interpreted it as such, taking the spectrum of the ambient noise and then just kind of having some kind of adaptive filters moving that stuff out. The other way would just be the time domain, kind of with that earlier code I showed you guys, is just like take the
Yeah.
average of the whole thing and zero it out for the baseline. But which implementation of mine, which interpretation is the correct one? Unless you're doing both.
I was planning on doing time domain, not the frequency domain. Like the time domain of like the ambient signals present and then filtering it down to that, like filtering that time domain level out. And even if I take like a 5-second sample, I was planning on like extrapolating that 5-second sample out to the length of each trial and then subtracting like it's sort of like as a mask then, right? So you could, if you extrapolated the sample, like the ambient sample out to like the length of the trial, then you could subtract like the trial data from the sample data to have like your clean like time domain filter data. That's what I was planning on doing.
All
Does
right,
that work?
that answers my question. Thank you.
Okay.
Like first question for me, but I'm gonna leave it for another time to talk about. It's usually better to take the frequency out and copy those over time, but we can have a conversation to see
Okay.
what goes. Dr. Tamina, no questions for them?
No, I think feature extraction, they're still gonna research on that, what feature is best suitable for this data, because again, things will change from
Yeah.
phoneme to, if you go to phoneme to vowels or, words. So again, it's gonna be a trial and error, to figure out which feature they would wanna choose.
Yeah, so so from here, you submit your CDR report, update your Gantt chart, I think is updated already.
Yeah, I keep trying to keep up.
Yeah, just make sure the last one that you send us is updated. So basically you're sending it to me and you're also sending it to your like mentors. All right, I'll give you so wait for me to give you the link of this video so you can put it in the same email, so you can keep it. The other thing that, so when you're preparing your to-do list, whatever is left from this semester that you push to next semester has to show in your to-do list. And that is a good way for me to know what should I get updated about the first 2 weeks of classes. Put the name of the person that's going to be responsible for solving that problem or, and bringing the progress to 100%. And then what's your timeline? Even though you have it on your Gantt chart, I want it to be extracted. So basically, the beginning of the next semester is going to be, let's remind also what happened, because we're all going to go for holidays. Like, if it's too fun, we're going to forget what happened. And then where we left off and what is our dates? Where are deadlines that we're going to hit this point? Capstone 2 usually starts with that. Like I changed it a little bit. So the first 2 week is continuation of the first semester. And then the rest of it would be writing your test plans. So I have the format, the document is ready. You just have to populate it. Depending on the project, the way that you populate will be different, but all of them will have tests and then test procedures, the test results and all of those. Now, think of, so in the first 2 weeks, so it will be one of your to-dos. What kind of tests you're gonna run, right? So, from physical, can I drop this? So there will be a drop test. Or no, you cannot drop the helmet, right? Can I leave it in a very, very cold room? Can I leave it in a very, very hot room? All of those are tests. How long the battery sustains on one charge? Those are the tests. So you see like where I'm going, so that's like all like physical. All the way to testing your software, testing your wire connections, you know, all of those. Sometimes you have to create a dummy test to test something. Like, oh, does this Wi-Fi like for like, I don't know, like I'm just gonna say the Wi-Fi. Does this, how far the helmet can be from the computer for the Wi-Fi to connect? That might not have anything to do with your test, but it's one of the performance, right? So create a test, so think about how we can test. Connect first, move it every 5 feet. Or that's one test, is this useful? Maybe the Wi-Fi stays kind of connected to it, or no. Connect at 10 feet interval, disconnect, move it, and is it able to connect at a distance, right? So these might not be directly related to what you're doing, but is one of the performance points. So one of your to-do will be thinking about our tests. And that first 2 weeks, I want you to think. Then when you're writing it, you're already thought about it. Does it make sense? All right, okay. So yeah, it was, since you explained everything and all these questions came up, which I think was like a different level of comment and feedback from last time, right? So a good presentation always gives you the opportunity to see the next layer of, you know, feedback. So congratulations on that. Everything was really good. So I don't have any question. John, if you have anything to add, please do so. Otherwise, I'm gonna stop the recording.
Sure. Main question would be, what is the next, assuming you guys come back ready to rock, what is each individual's next immediate goals for the project?
For me, it's working on getting those samples to the right, to what we want, getting to 500 samples instead of 3,000.
Well, I'm actually gonna overlay that. I think the immediate thing coming back for both Surya and Cole should be to set up a virtual environment so that me and Jason then can get used to the code and start getting help, so that way we can help on your guys' part instead of us being kind of in the dark with it at the moment, since you guys both are kind of running it off of your own local machines. I think that's the most important thing going forward for the two of you, at least. That way the two of us can start to get acclimated with the code. And then once that happens, then maybe me and Jason can see something in your code that you're not quite seeing that may be causing that 3,000 samples instead of the 500. I think that's the first thing coming back to hit the ground running. So that way, for me, it's then starting to become acclimated more with the code going forward, and hopefully being more like, now that like the initial project management and everything is kind of, now we're gonna be like really getting into testing and making sure like management's more gonna be like setting a whole bunch of stuff up. I think I should be able to be a little more hands-on and being helpful in the coding situation.
All right, kind of a follow-up on some of those points. What about software versioning control? How do you make sure that Cole's code and Soroya's code and Jason's code are all working together properly? You don't have the same names for the same file and stuff like that. Or do you have how are you doing versioning control? Are you doing a GitHub repo, a Bitbucket, or something else?
We plan on setting up a GitHub repo next semester. That's kind of what Sam was talking about. We haven't set up yet, but we want to implement that with GitHub and set up the repository.
All right, that sounds good. So excellent presentation, excellent progress, guys. So any other questions from Dr. Z or Kuzia?
So I think the next steps should be the integration, bringing all the pieces together. Once everybody has, you know, done their part.
Yeah.
Sam's part would be the integration piece.
Yeah.
Yep. But yeah, excellent work.
Thank you.